Hey everybody, welcome back. This is going to be day 3, session 1 of the Certified Ethical Hacker course. We're going to pick up just where we left off yesterday. And if we take a look at our slide that we left from, it was actually on the concept of Traceroute. So Traceroute's a program that we can utilize to detect the path that our packets take through a network. I think most folks coming into the class understand that, but they don't necessarily understand exactly how Traceroute goes about doing this. What they're trying to show us within this slide is kind of like what's happening, but I'm just going to go ahead and do it from a whiteboard. So one of the discussions that we get into in the networking classes is people commonly say, Traceroute uses UDP or Traceroute uses ICMP, and it's hard to really state, that either of those are true. ICMP, TCP, UDP, these all operate at which layer of the OSI model? Anybody know the answer to that? Which layer of the OSI model do these 4 protocols work at? And I've even had people dispute where ICMP works, but I promise it works at the same layer. Perfect. Yeah, this is all going to be at layer 4. And then, of course, at layer 3, you're going to have IPv4, possibly IPv6. And IPv4 is where Traceroute really works. Inside of an IPv4 header, there's a field called time to live. And every time your packet goes from one router to another. And it doesn't have to be a router. When I say router, you might think specifically like a Cisco router with a WAN interface. Any layer 3 device that's making a routing decision. Could be a load balancer, it could be a firewall, it could be a layer 3 switch, could be a traditional router. When you make, and let's say that this PC sends the packet out, whenever you send a packet onto the wire, you've got a layer 2 header, right? Typically it's going to be your Ethernet header. And he's got a source and destination MAC address. The source is that of the PC's network interface card. The destination is typically going to be your default gateway if this packet's headed off network. And then what happens when you make that layer 3 forwarding decision on a router is that you get a new layer 2 header. Is everybody familiar with that? And again, if this was an Ethernet link, you'd have sourced from, let's say, router A, destined for router B, and then again, at the next router, you'd have a layer 2 rewrite. Does this feel familiar? Eric says, yeah, cool. So every time that layer 2 rewrite occurs, we're basically taking a hop. That's what hop truly means. You're moving from one network to another. And what we use the TTL for is to define a maximum hop count. Now, the highest that this field can go, being 8 bits, is going to be 255. So the max TTL is going to be 255 hops. Different operating systems will sometimes use 128, sometimes use 64. And that knowing, what we start off with a TTL can be used later when we talk about passive OS fingerprinting. In other words, if you were to look at network traffic, we talk about this passive versus active reconnaissance. I could use Nmap, and I could send lots of kind of probing packets, weird packets with strange collections of flags, just to see how the remote host behaves. And based on that interrogation, I could make a good estimate of, that's a Linux host or it's a Windows host, maybe it's Windows 8 versus Windows XP. I can start to kind of dial in based on how TCP behaves. That would be active because we're probing it. Passive OS fingerprinting is just passively watching traffic go by, like with Wireshark, and looking at different things like the initial sequence numbers used in a TCP handshake, whether or not the don't fragment bit is set, what TTL do you start with. There's a number of different things that you could look at in terms of just the behavior. But for the most part, when we generate this TTL message, it's to guarantee that if we ever found a routing loop, where one router says your destination's that way and the other router says your destination's that way, they're both just going to ping pong the packet back and forth until that TTL drops down to 0. At that point, you get a message that comes back that says your TTL expired in transit. So in summary, your TTL's a loop prevention mechanism, and when it times out, if it goes, every time we cross a hop, it goes, let's say 128, 127, 126, 125, eventually, if it hits 0 before reaching the destination, you get an error message back that says, sorry, buddy, your packet didn't make it. So what I love about Traceroute is it's really, truly hacking. They took something which was just a loop prevention mechanism, and if you run out of hops, you're going to get an ICMP message back that says your message expired in transit. So if someone were to say Traceroute uses ICMP, I would say yes, for the error message. And it's these error messages that we use for actual path discovery. Now, the outgoing packet, it really doesn't matter what you have at layer 4, does it? Because all we're really concerned with is looking at your IP header and specifically looking at the TTL field within it. This is just a hack on this operation. You see, what we do when we run Traceroute is we send out IP packets, but we'll set the TTL to 1. What happens if the TTL is 1? How far is it going to make it? It gets to the first hop, right? It gets to this router, and when he goes to make the hop, or the layer 2 rewrite from one Ethernet port to another, he decrements the TTL. When your TTL hits 0, he sends back that error message saying, sorry, buddy, your packet didn't make it. So the way that Traceroute works is we send out a packet with the TTL of 1, and we discover the first hop. Then we set a TTL of 2, and we discover the next hop. Then we set a TTL of 3, and we get the next hop. Does that make sense? How many of you just learned something? Let me know if you learned that new, or if that was just something that you already knew. Just let me know in room chat. Say knew it already, or that was useful. Already knew it. Okay, great. Cool. Well, we're gonna go in layers here. We're gonna get to firewalking and TCP traceroute. Some people say it's new. Some people say they knew. I love it. Okay, so let's go ahead and we'll build on this a bit. All right, so that's just regular old traceroute. Now let's get a little bit fancier with it. There's a technique in networking called PBR, and it's not Pabst Blue Ribbon beer. It's policy-based routing. What that means is when a packet comes in, I draw my packets as envelopes. What we normally do is we look at the destination IP of a packet, we look at a routing table, we make a forwarding decision. Policy-based routing is looking at more than just a destination IP address. We could look at the source. We could also look at the layer 4 header, which is very much like an envelope as well. It's going to have source and destination port numbers, at least if it's a TCP or UDP packet. So using policies, service providers, hotel networks, and anybody providing network services to, say, the public or to users could apply different policies. What I mean by that is they might send your DNS traffic in one direction, they might send your HTTP traffic in a different direction, and they might send your SMTP traffic for when you're trying to send mail out in a different direction. Does that make sense? So you basically have an if-then agreement on your router that says, hey, router, if you see packets destined for TCP port 80, set the next hop to some other destination. So this is ultimately more specific than if you were to just use traditional destination routing. So what's cool about this is when performing traceroute, we can detect the hop-by-hop path we take through a network. When performing TCP traceroute, and this is why I'm always hesitant when people say, well, what does traceroute use? I say, well, it uses ICMP for an error, and it uses IP to elicit the error, but you can get fancier. Using TCP traceroute, which you can install on all the different Unix distros, whether it's Linux, OS X, etc., there's typically builds of this. I can do a traceroute which says, hey, show me the path that I'm taking to get to this destination IP address on port 53. And I could show me the path that I'm taking to get to that destination IP address on port 80. And what this gives you the ability to do is kind of look through the network that you're going through. We call that the transit network, and we can discover policies that are being applied to your traffic. Is everybody comfortable with that? In summary, TCP traceroute can be used to discover the path that specific traffic flows are taking. This is really useful if you want to see if your web traffic is being redirected through some type of proxy that you don't know about. I had a situation where I had to figure out that email traffic was being relayed through an additional agent. And it was kind of neat. If I did a traceroute to my house for HTTP, it was 11 hops. If I did a trace to my SMTP server, it was 4 hops. I was like, wait a minute. what's going on here? And it was like they were taking my traffic through some type of tunnel or something, but I could notice that I was going through a completely different path to get to the same IP address on a different port number. You wouldn't normally know that. So TCP traceroute is an enhancement to traditional traceroute that allows us to detect various paths. How are we doing? On a scale of 1 to 5, 5 being you're feeling really comfortable, 1 you're completely lost, how's everybody doing? 5, awesome. All right, we're going to go one level deeper then. We're going to introduce a concept called firewalking. And this isn't something I use real often, but it is something that typically comes up on the test. So we want to understand it for testing purposes. Firewalking is using traceroute to determine what's happening behind a NAT gateway. So for example, you've got the internet, connected into the internet is a target's firewall. On this firewall, they're probably performing network address translation, and more specifically, they're probably doing network address translation specifically with port numbers. So they sometimes call that NAT PT, or simply PAT or port forwarding. In other words, we listen on port 80, and if it comes into some public IP address, and I'll just use Google's DNS server for example, 8.8.8.8. If it's coming into 88888 on port 80, we're going to NAT it and put it to the internal IP address of 10.1.1.80, and again, we'll forward it to port 80. So far, so good. Now, the thing that's interesting is a lot of times organizations will do this for multiple services. So you can have a single IP address that's public, and you could use that single IP to NAT to different services. For example, I might have a SharePoint server on Microsoft Windows, and that's what I'm forwarding people to. And if you were to come in on port 53, I'm going to send you to my bind server for DNS. And this is actually 10.5.5.53. So assuming a /24 mask on each of these networks, what's going to be happening there is that even though we're listening on the same public IP, we could go to 2 different internal addresses. Is everybody comfortable with that? Cool. So let's say that we plug into a switch. Our switch could plug in directly to the DNS server, but before you get to the web server, you may have a device like a Blue Coat proxy or some other type of web application firewall, or maybe an F5 load balancer. Well, this would be an additional layer 3 hop, and what he might be doing is taking this IP address of 10.1.180, and this could even be multiple hops, right? You could have another VLAN, so we take a hop across, from one VLAN to another. And then when you get to that device, he may be load balancing or proxying in some way. So firewalking is the process of using TCP traceroute, which we just learned, and we're going to the same IP address. In this case, I just made up the IP of 8.8.8.8, and I see that if I connect there on port 80, maybe it's 11 hops. And if I connect there on port 53, it's 9 hops. So what this would indicate is that beyond the NAT gateway, that there's going to be some type of internal filtering that's happening. Does that make sense? There's some type of internal device that they're passing you through. There's another hop inside of the network, and we're figuring that out by looking at the TTL. Everybody still feel comfortable? Awesome, we're doing great, man. Very, very cool. Now I'll show you one last thing. This is a little bit tricky. Number one firewall in terms of not performance, but just the number of units deployed is Cisco ASA. So you might like Palo Alto, you might like Checkpoint, but there's a lot of these boxes out here. A lot of guys that come to my ASA class come to the ASA class and they bash ASA and they say Checkpoint's the best firewall. I go, what are you doing here? They say, well, we bought Cisco because it's cheap. And in comparison, Cisco is cheaper than a lot of the other vendors, and that's why some people use them. I think it's funny. But statistically, you have a very good chance if you're doing a penetration test or audit of encountering an ASA. Since we're on the concept of traceroute, what you want to know about is that when you go into an ASA and you look at the way he handles traffic, It's not going to let me do it like that. Let me create a new policy real quick. Whenever the ASA passes IP traffic, I'll just match any packet. He does something that's a little nasty, and that is he doesn't decrement the time to live. So we just learned that whenever a device crosses a layer 3 boundary, so you go from one network to a network, we've got the layer 2 rewrite, that we decrement TTL. Well, the ASA, by default, tries to behave in a stealthy manner, and he doesn't do this. If you want him to, you have to identify a traffic flow, like traffic from the admin network going anywhere, and I would say for that particular traffic, decrement TTL. But by default, he doesn't do that. Another thing, since we're on the concept of TCP fingerprinting, when looking at two applications, when a TCP session comes up, we have a 3-way handshake. The whole reason for that 3-way handshake is to negotiate initial sequence numbers, right? I'm going to start counting at 1025, and you acknowledge that, and then you send me a SYN that says you want to start counting at the number 1. I acknowledge that. We're good to go. We can now send data back and forth. Our data is basically going to have a number on it, a sequence number that says this is where it goes within the flow. So if we have asymmetric routing or we've got any type of load distribution and packets arrive out of order, we can use the sequence number to put them back in order. Well, the ASA does something kind of freaky as well. It's called TCP sequence number randomization. So if you try to do a 3-way handshake with a device that's behind an ASA, he's going to fuzz those numbers. You know how we do NAT? He's basically natting, which is just a rewrite, but instead of doing it in the IP header, he's doing it in your TCP header on the sequence numbers. So you're trying to probe a server, and you're using Nmap, and you're using OS detection. If that server is behind an ASA and your OS detection is relying upon TCP initial sequence numbers, this sequence number scramble is sequence number randomization is going to scramble that detection process and give you bogus results. Just some kind of behind the scenes info. So we talked about Traceroute, which we opened up with. We said this is a way to detect a path. It's based on receiving ICMP error messages back. Those ICMP error messages are going to be sourced from a router, and we're basically learning who it is, right? So if our first router is named router 1 sends us an error message back, and I go, cool, that was the first hop, this IP address. What was the next one? What was the next one? So we figured out Traceroute. We said TCP Traceroute will show us policy-based routing that's occurring inside of an organization. So if certain traffic is being redirected through some type of inspection engine, we could detect that. You could even detect it behind the firewall through tools or a process called Firewallking. Cool. So that was Firewalking. The last piece I wanted to show you was the ASA, which is one of the most popular platforms for firewall solutions, does a TCP sequence number randomization, which is going to make your OS fingerprinting a little bit unreliable, and it also doesn't decrement TTL, which is going to make your traceroute a little bit less reliable. And also realize that it could be turned on if the administrator created a policy to do so, but it's not on by default. Just good things to understand about Traceroute. All right, that was a whole lot of Traceroute. Was that cool stuff or not really? We're still in the process of, just kind of learning how to map out an environment. We're looking at footprinting. When you think about footprinting, this is what the bank robbers do before they rob the bank. They want to know where the security cameras are. They want to know what time the armored truck shows up. They want to know how many tellers are working, when they take their lunch breaks. Is there a guard on site? It's just putting together that information so you can have a more successful attack. When you look at a traceroute analysis, what you're basically seeing is the sequence of events between the attacker and the victim. Which hops are we crossing? Which types of devices? Now, typically your traceroute output is going to be based on just a command line tool. You're going to see a series of IP addresses returned. There's GUI tools as well, like Visual Route, and it'll actually do a GeoIP lookup on each IP address and build you a graph showing you, geographically where you're connecting through. There's another utility for traceroute called MTR. And if you haven't used this, very, very useful. MTR is traceroute and ping all in one, and it keeps running in a loop again and again and again. This is a little bit better for network troubleshooting, but you can use this if you actually do get into a target. So here's the attacker, here's the victim. If you are installing software on that victim system and you want to see the return path, you might do a trace route from the victim to the attacker and compare that to the trace route for the attacker to the victim. And many times you'll see that you have asymmetric routing, which indicates you've got some other type of device sanitizing outbound traffic that could be looking for certain types of threats or call home procedures that are being used by a backdoor or rootkit. So understanding what's happening with your network traffic, extremely valuable. MTR is an excellent utility. Not only does it show you trace route, but it also shows you latency on a per hop basis. Footprinting through social engineering, this is going a little bit further, but this is talking to people and conning them into giving you more information. As far as what you should know for testing purposes, and I guess just real world, shoulder surfing is simply looking over somebody's shoulder, trying to detect what they're, trying to monitor what they're typing in. Dumpster diving is just going through their trash, looking for anything that's been thrown away, maybe backup CDs or pieces of paper with IP addresses or passwords written on them. Don't have a lot to add there. We talked a bit about social networking sites yesterday, Facebook, LinkedIn, Twitter, etc. I think most of that's pretty obvious regarding what you can get. Now, the key that we're starting to see, or the pattern that we're starting to see at this point, is that there's a ton of information out there, and we just need a good way to collect and organize it all, especially if you're working with multiple people. If you're working with lots of other folks, you're probably doing the same types of scans and collecting the same type of procedures again and again. So you could use a framework to organize that. One framework that you can use between multiple pen testers, it's not covered in the class, but it's a good one to know about, is called the DRADIS framework, D-R-A-D-I-S. Alternatively, you can get all this information, and some people, they just throw it into like a paste bin file or text file. Other people like to visualize it. There's a application called Maltego. Have any of you guys had an opportunity to mess with this yet? Just let me know in room chat if you have. Maltego has the ability to take in information like an IP address or a company name or an individual and run transforms against it. What a transform is an operation that tries to resolve other data, such as taking a host name and turning it into an IP address, or taking a person's name and seeing what domains they have registered or companies they have registered. This tool, you'll supply it a piece of information like my name, Ryan Linfield, and then you could say, what domains does Ryan Linfield own? And then you could say, what business is he involved with? Where's it geographically located? And these transforms are just different types of lookups. But as you build them, it creates lines and connections between different related entities, and then you can run transforms against those entities. So I could say, for example, show me websites that have stormwind.com involved. So it does a bunch of lookups, comes back with a couple websites. I say resolve all the IP addresses, and it might say we had 8 different host names, but they all resolved to the same IP. Well, I could right click on the IP and say show me where that's geographically located. And you go, okay, cool. And you just put that data to the side. Now you could come back to your stormwind.com and look it up. You can say who owns stormwind.com, and it could say Tom Gronke. You could right click Tom Gronke, who's the owner, and you could say what other organizations is he involved in, and it could do lookups, and it could say he owns these other domains. And I go, cool, what IP addresses do those resolve to? Different IPs. Where are they geographically located? Same data center. So it gives you ways to just look up tons and tons and tons of information and then visualize how it's related. Does that make sense? This is, they're getting a community edition of this tied into the new version of Kali. A new version of Kali is coming out, I think, August 12th. It should happen after DEF CON. And it's going to have a community edition of this built into it. All right, so footprinting countermeasures. So this is pretty dangerous. Has everybody Googled themselves? Lots of information about you out there. Maybe it's valid, maybe it's invalid. Anybody can find it. Well, one of the easiest countermeasures to these footprinting attacks is putting out information that's bogus. So if somebody's trying to look up information on you, let's just give information that's misleading. We could have fake names maybe registered under our domain, right? So if you do a domain lookup for me, maybe there's a real technical contact or administrative contact, but the other 2 names are bogus. And if anybody ever calls asking for those names, I'd immediately know that that was something that was no good. Alternatively, there's a lot of things you could do along the lines of misinformation. One that I've done in the past that I think is kind of fun. Let's take a look at DNS mining for a second. Come over here and let's cancel out of the ASA. And okay, I have about a dozen different passwords. So when things don't work, this one. All right. So one of the things that we can do when we're footprinting, one of the first places to start is a DNS scan. There's a Perl script you have for this that's built into Kali called Fierce, and you don't necessarily have to use a Perl script. You can do DNS mining just by writing a pretty simple Python script and referencing a word list and doing a bunch of recursive lookups, and you can even multi-thread it. If you're interested in learning how to do that, there's a book called Black Hat Python that really walks you out. This is how you make a 4-line Python script. Here's how we add 2 more lines to make it more powerful. Here's another 2 lines to give it some sorting. And before you know it, you build a full-blown program. Fierce is just a Perl script that someone else wrote that gives you ability to do DNS mining. What that would look like, we could do Fierce minus DNS, and we can do a lookup against stormwind.com. So this is one of the things that people will do, when they're trying to map out an organization. And here you see like there's a sales, there's a www.promo.stormwind.com, there's server.stormwind.com, staging, and you see the relevant IP addresses here, right? So why would anybody go to, let's say, test.stormwind.com that isn't involved in the organization? Or the vault.stormwind.com. That looks that looks enticing. We might want to click on that. Well, if you want to protect your organization, you could just put some bogus assets in here that aren't really being used. And when you come over here to the IP addresses that they point to, well, there's various, let's just bring up Chrome real quick. And you can put do not scan list. And you'll find IP addresses that belong to like different government agencies. And here they're just showing you entire Class A blocks. So MacDill Air Force Base, that's right up the street. So this would be located in Tampa, Florida. So I can start creating assets from my company. Say it's mycompany.com. I could have the vault.mycompany.com located at 126.216.115.34. And what that's going to do is hit the /16 network that's assigned to MacDill Air Force Base. Anybody else know what else goes on at MacDill Air Force Base? Besides golfing? And an air show? Some of you guys were local, right? This is where Central Command, SOCOM, and Cyber Command are run out of. So if somebody's probing me, I don't have time to chase down every attacker, drone pilots, all that type of stuff. I don't have time to chase down everyone. But if part of the attacks that are coming in at me are also hitting a military base, maybe they've got somebody else looking at them. So what you could do is just create additional DNSA records that provide information that looks like it would be promising, but it's pointing to perhaps other people's networks. Now that's not really ethically the best practice, but you could put misinformation out there for other people to find, and it's just extra data that they've got to sort through. All right, so additionally, you could just kind of limit what information that you put publicly, not disclosing the particular features or services that you're using in your organization. One of the things we talked about was job sites, right? We said on a job site, if you if you post an opening and you say somebody must know Cisco ASA, SourceFire IPS, ArcSight, they're going to know exactly what you're using. If they wanted to attack your SIM, SIMs have vulnerabilities as well, so they would know what they could use if they could find it and would have known already from the login screen. But it just gives people more additional information. The flip side of that, which is pretty neat, are targeting recruiters. This was something I heard from somebody in my DEF CON group. By targeting job recruiters, if you can get your hands on all their resumes, and then they have an internal database where they stick all the candidate resumes in, and those resumes are in a searchable format. So if you can get as an attacker, if you were able to compromise someone's account or get their access into a resume database, you could look through employees' previous job history, right? So let's say that I was targeting Disney World and somebody used to work at Disney World. It would say, when I worked at Disney World, I was responsible for the maintenance administration of F5 load balancers. You know, we had a big Citrix environment. We did this and this and this. So they'll put it into the resume. So people's existing resumes, which you can also look for online, could disclose information about a target. So that's probably enough on footprinting. Let's start working towards scanning. All right. Let me just pop back over here for 2 seconds. How are we doing so far, guys? Any questions? How's the pace? Good so far, no questions? Are we still having fun? I hope everybody's learning a little bit, right? There's, you know, almost 20 people, so we've got different backgrounds. I hope I'm going at a good pace. So let's take a look at network scanning. The baseline of network scanning, thinking about public subs, yeah, boy. Checking, when we do network scanning, the first thing that may come to mind is like a ping sweep. So an ICMP echo request just says, hey, are you there? And somebody comes back with an echo reply. What's the problem with ICMP echo request and echo reply? How reliable is this today, 2015? I mean, it's pretty reliable, it's ping, but you may have a host that's up that just simply doesn't reply. ICMP could be filtered. So the way that it used to work historically was you'd script all these attacks. You'd say, do a ping sweep of this subnet, and then you'd take the report for all the hosts that are up, and you'd feed that maybe into a text file, and then use that text file as a source for the next line in the script that says, you know, go ahead and do a port scan against everybody that did, you know, this ICMP echo request. And then if these ports are open, maybe you launch attacks or you try to do, login attempts against those ports. So at the beginning of the script, the first thing it checked for was an echo request. If you didn't reply to that echo request, your name or your IP address really wouldn't wind up in the text file of devices that get the port scan, which wouldn't wind up in the attack script that, you know, is this port open? We're going to try to log into it. So what people started doing years ago was blocking access to ICMP. So what you can do today is kind of neat. Even on some network hardware. Let me see if I've got mremote installed. I do. So when you ping, and again, this is going back to an ASA, look at this. Did you know you can ping using TCP from some Cisco devices? And the idea is if you type ping by default, it'll use ICMP, but you can also do a TCP ping just to get around this. A TCP ping is simply sending, you know, if we suspect a service is open, we send a TCP SYN to a common port like 80 or 25 or 445 if it's a Windows host or 443. And the idea is that that may get a SYNAC where the ICMP would just be discarded. Any questions on ping versus TCP ping? Ping doesn't always work. As an alternative, you can do TCP ping, but you've got to have a good port. Ping sweep is simply going to every IP address within a range, seeing who's up. Nmap's a common utility for this. What did we learn a couple days ago about Nmap doing a ping sweep to a local subnet? How is that different from a remote subnet? Anybody remember? Showed you guys this on Monday. I did a ping sweep of my local subnet, and I was using Wireshark looking for ICMP traffic, and I didn't see any. Perfect. If it's your local subnet, he doesn't send ICMP because he can send ARP. There's a utility called ARPing, which you can use to do the same thing. It's just neat that Nmap does this by default. If it's the local subnet, using ARP is going to be more reliable than ICMP. So we just have to have a device that's on that local subnet. Other ping sweep tools, there's a utility for Windows called Angry IP Scanner. Runs pretty quickly and aggressively, thus the term angry. Also will tell you the host name and try to determine that ports are open. It can resolve the MAC address if it's a locally connected subnet. And then within SolarWinds, this is a network tool set. There's a capability in it to do things like ping sweeps as well as an SNMP browser. So let's take a look at TCP. Moving away from ICMP, we know that TCP uses a three-way handshake to establish a connection. The reason we do that, we send a SYN, which is short for synchronize, and it says, I want to start sending you data, and I'm going to start with the sequence number at 10. What the responding device, in this case our server, does is he acknowledges our sequence number with an acknowledgement of 11. And he tells us, I'm going to use sequence number 142. So this is why you send a SYN, you receive a SYNAC. That's an acknowledgement to your SYN or synchronization request, and they're sending you a SYN saying this is the number that I'm going to count with, 142. And then I acknowledge their 142 with the 143. So far, so good? We're just building in layers here. So when you look at TCP, he's different from UDP. One is the fact that he's got this sequence number that we have to calculate. Why is that? Well, we have guaranteed delivery. If something doesn't get to you, you can request that I retransmit, and I'll go ahead and do that. Every package that I'm going to send you is going to have a number, and we know whether it got there or not, making it very reliable. Now, TCP has different communication flags for whatever it is that we're trying to do. The common ones that we know are SYN and ACK, because that's what's used to set up your session. At the end of a session, you'll see a fin and a reset. So fin says, I'm done communicating, and reset tears it down. Additionally, this should be ACK here. Additionally, you've got a push, which says send all of your buffer data immediately. And you have urgent, which is a flag that says this should be processed immediately. What that boils down to is you've got a TCP header, looks something like this, like source, destination, port numbers, sequence numbers, acknowledgments, etc. Within here are TCP flags. The reason we care about these TCP flags as an attacker is because different systems have different TCP IP stacks. And by sending these flags out of order, remember that TCP is a standard. There's an RFC that defines how it works, but still, when people, engineers, read these RFCs, they sometimes interpret things differently and just do things a little bit differently. So as attackers, we can look for differences in different vendors' TCP IP stacks. That's what we use to identify what the operating system is. So you can use a custom packet crafting utility to basically send a TCP packet, and we can fraudulently populate these flags. So if I want to spoof a packet and say that it's coming from a different location, like Google's DNS server, I just fill out the source IP address and I say that should be 8.8.8.8. When it comes down to my TCP flags, I can turn them on and off with a mouse click. The reason that you might want to do this is just to probe different devices and see how they behave. I've created a pretty large number of different denial of service attacks against network infrastructure, IPSs, firewalls, switches, routers, all just coming in here and creating conditions that shouldn't normally be possible. You know, they'll say things like, you can never have a packet that, you know, has all the flags set at once. I go, sure I can, and I can set every TCP flag to on. And they can say, you know, source address should never be a broadcast address. Well, sure, I'll just put the source address as 255, 255, 255. And then, you know, you send it to a device and you just see how it behaves. Some devices don't know how to handle it and they'll crash, and that's simply a denial of service condition. I talk a little bit about this. I did a talk at B-Sides called Igniting Firewalls, and I didn't actually release any 0 days because I might want to work at Cisco someday. But I talked about what I did to find those types of vulnerabilities. So if you go to YouTube and you type Igniting Firewalls, you can see a bit more about that. As far as a scanning tool, your de facto scanning tool for ping sweeps and port scans is going to be Nmap. It can not only determine that the host is open, it can tell you what services are listening. It can try to identify the services that are there. It can determine the operating system. And it even has some light capabilities to do vulnerability scanning. HPing And hping2 are custom packet crafting utilities. They run from the command line. And once again, this gives you the ability to set the attributes that you would want inside of a TCP IP packet. So I could say I want to use these flags, I want this as a source IP address. This is really handy when you're trying to make custom packet conditions that shouldn't normally exist. Or if you wanted to spoof a bunch of packets and make them look like they're coming from somewhere, you can build the packet with hping, which is a little bit of a pain. The arguments for it aren't that intuitive. So it might take you 10 minutes of putzing with it to create the single packet that you want. The cool thing is you could capture that packet with TCP dump or Wireshark. And when you do that, it'll just output it as a PCAP file. Once you have that packet capture file, which is just like a text file or a JPEG or anything else, you could replay it with TCP replay, which is a third utility. TCP replay lets you take a PCAP file and send this, whatever those packets are, out onto your network interface. So I'll typically build the custom packet with hping. I do all my experimentation there. Once I'm done, I'll capture it and I'll just use TCP replay to use that same packet in the future. Or you could just copy the string or argument that's used to a text file. So let's take a look at scanning techniques. This is something that's been a heavy testing point over the years with CEH. See if I've got slides on each of these. Yeah. So there's different scanning techniques we're going to talk about, like SYN scans, Christmas scans, fin scans, etc. And these are going to build in complexity. So the most common scan type that we do is called a TCP connect, also known as a full or open scan. Basically, you send a SYN to a service on a particular port. If you send a SYN-ACK, we can come back with an ACK and a reset. In other words, we're basically just connecting to that device, and we want to see whether or not it's open. And they actually described this wrong in the slide. Kind of. So I'd ignore the reset for now. We do tear it down, but we do actually complete the three-way handshake. Let me show you the difference. In a TCP or full connect scan, three-way handshake is completed, meaning you send the SYN, you get the SYN-ACK, and you send an ACK, and then after the ACK, it's torn down. But the three-way handshake did complete. In what we call a stealth scan, or a half-open scan, you send a SYN, and when they send a SYN-ACK back to you, you tear it down. So in that scenario, the three-way handshake did not complete. Is everybody okay with that? You see the difference? We didn't complete the three-way handshake versus we did. When they first introduced this, they said, here's this new stealthy thing we can do to not show up as having built a full connection in the operating system logs. And we go, oh, that's clever. But they were talking about this like publicly. So, a couple weeks later, all of your IDS vendors have signatures that say, when I see a SYN, a SYN-ACK followed by reset, this is a stealth scan. So in most scenarios, the stealth scan will actually get logged and create an alert on an IDS, where a full connect scan will not. They don't tell you that in the book. As far as the book and the test are concerned, this is what you can use to bypass firewall rules and logging mechanisms and hide your traffic. But in reality, this is probably going to make more noise than a full connect scan. A Christmas scan is where we send a TCP packet and it's got the fin, urge, and push flag set. And we say it's lit up like a Christmas tree. Well, this won't work against current versions of Windows, but it will work against versions of Unix. The idea is when you send it to a server and a port is open, you don't get a response. But if I send fin, urge, and push to a server and I receive a reset, it means the port is closed. So this is called inverse scanning. A lot of times what would happen is we might do a Christmas scan against a collection of ports from, let's say, like 21 to 25. That's pretty juicy. And what happens is you only get a response, which is going to be a reset for port 24. If that's what happens, if this is my scan and this is what comes back, which ports were listening? All but 24, perfect. So 21 was listening. What's port 21 for? I'm going to ask you 22, 23, and 25. So let's see, 21 is going to be FTP, 22 is going to be SSH, 25 is going to be SMTP. For Simple Mail Transfer Protocol, 23 is going to be Telnet. We should know this type of stuff for the test. Not only is it great bar talk, the ladies love this stuff, but also definitely testable. All right, so fin scan. The fin scan is where you send a fin, and if the port is open, no response. If it's closed, you get a reset. Fair enough. Doesn't work against Windows, works well against Unix. Now, is that always the case? Not really. Let's talk about why. If I know that a server is a Linux server, how would I know that? Well, I don't know. I connect to the server on port 80. I get an Apache greeting screen that's kind of like the default installation, and it's got something there that hints to the box being Linux. I could go, okay, since I know that this is a Linux server, a fin scan should work, right? So if I send a fin to port 80 and it's open, I shouldn't get anything back. If I send a fin to 81, I should get a reset because it's closed. Agreed? Just taking what we learned in the last slide and applying it to a new situation. If I've determined that the box is a Linux box, I can use this fin scan and this should be the result. Well, a lot of times what people will put in front of their web server is a what? Like if the internet is here and the web server is there, what might be in the middle? Do we just plug it in directly? Good, firewalls. Well, there's all different types of firewalls. Maybe reverse proxy, who knows? So our question could be, what type of firewall is this? Now, I don't mean is it Checkpoint or Palo Alto. I'm asking, is it stateful packet inspection? Or is it a simple packet filter? What's the difference? Well, packet filtering is what we see with the typical router when someone wrote an access control list and they're doing port filtering. All that an ACL does is look at the packet. It looks at the layer 3 and layer 4 envelope, meaning it looks at IP addresses and it looks at port numbers. And if it sees things it likes, like port 80, let it through. If it's not port 80, drop it. So packet filtering just does this. Stateful packet inspection, of course, still uses ACLs, but it also performs, as the name suggests, stateful packet inspection. In other words, he looks at the TCP sessions, and you have to do a three-way handshake. And once you do a three-way handshake, that connection goes into a connection table and is going to be monitored. This isn't any type of bleeding-edge technology, but it's a major difference between simple packet filters, which people still use, and a modern firewall. If something is doing stateful packet inspection, it could possibly be doing deep packet inspection, which says if you see something at layer 4, let's say this is a TCP header, and it's going to port 80, open up the contents, and let's look at that payload, our layer 5 through 7. And he can use an HTTP inspection engine, possibly. Like this is what your ASA, Checkpoint, and Palo Alto are going to do. So I can expect that a target is going to have a firewall, but I'd like to know, is it a really crummy, just very simple packet filter firewall, or is it stateful packet inspection? I can determine that pretty easy using this type of scan. Can you imagine how? How would a stateful packet inspection firewall deal with a fin scan? It'll drop it because he didn't see the three-way handshake first. He says, do we see a three-way handshake? No. Silently drop it, so you'd never get the reset. So using things like ACK scans or fin scans is when you just send an individual ACK or a fin or even a SYNACK and you're just trying to get a reset. And if I think there's a firewall or some type of device in the middle, which remember, these guys try to be slick. He's not dropping the TTL to try to hide his presence. But by testing for stateful packet inspection, I can go, cool, we've got a device in there that's looking a little bit closer. Let's be more careful. So some of these tools are great because they can be used to say, okay, that's a Windows host or a Linux host based on how it handled this particular message. But it could be like, we could think it was a Windows host when it was really Linux because stateful packet inspection was dropping this. A NULL scan is super easy to remember. If you get a question on this on the test, this is like free points. What flags are set in a NULL scan? No flags. It says, I'm going to send you a TCP header with no flags set. You go, that shouldn't happen. And I go, well, we're just doing it to see how the remote host behaves. And it's one of those situations where if the port is open, you don't get a response. If it's closed, we might get a reset or ACK. All right. We've got, how are you guys doing? Everybody keeping up, feeling energized? Your brain doesn't hurt yet? I hope. Dude, Bob's doing good. Okay, awesome. Jake, everybody's keeping up. All right, here is where we're going to do some packet kung fu. All right, so let's say that there's... okay, so when I want to scan a system, let's say that I'm on a wireless network at the airport, and I want to look around and I see that there's... let's make this interesting. I'm on the public Wi-Fi at the airport, and I know that there's a router, .1. But I'm curious, what service is the router's running? You've got all these people hacking airplanes now, and FAA doesn't have much of a sense of humor. So when we look at, probing Wi-Fi networks in an environment where they could actually be watching for things like port scans, you might want to be really, really careful about what you do. So what we could do to do a port scan but not have it come from us is find, what do they call is it a patsy that they use in the financial scams, kind of like the clueless guy that doesn't really know what's going on? You find your patsy, or you find your kind of clueless host. So here we are, we're on a network, and maybe somebody's smartphone joined the network or their tablet, but it's not really doing anything. So if I can go, okay, .1 is the gateway, I've got a hunch that somebody might be monitoring this, that they may have some type of logging engine that's watching for scans. So what I could do is bounce a scan off somebody else. I could just do some regular ARP, and I could pace it out slowly. Slowly is what's going to keep me from being detected. So just ARP for different devices in my environment, maybe sending out one ARP to a different IP every minute. Shouldn't look suspicious at all. IP addresses shouldn't be changing that often. What I can do is use ARP to learn an IP address to MAC address mapping. What's neat about that is by looking at the MAC address, a MAC address is 48 bits in length. The first 24 bits are called your organizational unique identifier. It lets me know whether it's an Apple or Samsung or Nokia tablet, whatever. So by looking at ARP cache, I can identify different types of devices, and then I can find one like, say an iPhone, and I go, I don't think anybody's got a port scan engine, like a monitoring agent on their iPhone, no type of software firewall. So I can look for some commonly open ports on an iPhone. I know it's an iPhone based on the OUI. And if there's a TCP service that's listening, I can send a SYN, and he's going to send a SYN-ACK. Agreed? At least if one port, any port is listening. Maybe it's a discovery service. Could be TCP or it could be UDP. Now, we're going to get a little bit deeper into packets. We talked about the IP header, right? I said the IP header is just an envelope. Let's take a look at it. Come over here, let's pop up Wireshark. And I'm going to show you a pretty neat utility. Now, this is something that, let's not update right now. This is something that gives you the ability to do stealth scans. It's a little complicated, but it's very cool. So I've got a bunch of traffic going on because I'm streaming my desktop. So I'm going to stop this, and what we want to look at are packets coming from one computer going to the next. And when you look at packets in Wireshark, if you're not familiar with this, you've basically got three major windows. The top window, which is this kind of purple window that I'm moving the mouse up and down over, is going to be our packets. Over on the left-hand side, since I started my capture, I got 32,000 packets. See the number? And you see how it increments? And the time shows you how long the capture was running. So 10.2 seconds into my capture, this is what I saw. Here's source and destination. So that's just a collection of packets. When you highlight them, you can look at the details below. Here's your Ethernet header, which is layer 2. Here's your IP header, which is your layer 3 header. Notice source and destination IP. Here's your TCP header, which is layer 4. So it takes all that intangible stuff and it actually just lays it out for us really pretty. Now, what's cool about this is we can look inside of the IP header and get to know it a little bit better. One of the things your IP header has an IP ID. I imagine some of you guys have seen Wireshark before. How many of you are familiar with the IP ID? And I'm curious because some people are going, what the heck are we getting into here? And other people might say, of course, yeah, the IP ID, look at it all the time. I don't know. Anybody familiar with this? Nope. This is pretty neat. This is something that goes on in every single packet that going on the internet, right? But what's neat is look how the number is 16807. If I go to the next packet, 16808. The next packet, 16809, I hope. And it was 16810, and then it jumps all of a sudden, but that IP ID was a response coming from someone else. It was from 63 back to 62. And if we look at his responses, see all these messages coming back from 63? See how they go in order? So all the packets that are going in order that are part of the same flow are going to have the same IP ID. If that target that I was talking to was talking to a bunch of different people at once, imagine BitTorrent, right? You could be talking to tons of people. You may not get that sequence of one packet after another. That's why we call this type of attack an idle scan. Watch how this is going to work. I'm on the airplane or I'm at the airport and I scan, and let's say that I hit somebody's iPad. And it's not really doing anything. They're just reading a PDF. So I can send a TCP SYN or I can send a UDP message that elicits a response. And then when the response comes in, I can note the IP ID. Does that make sense? So I'm just checking that target to see what his IP ID is. Why on earth would I do that? Because if there's an air marshal, I want him to come talk to that guy and not me. Watch how we're going to do this. What we're looking at is a concept called an idle scan. It's based on the fact that most network services listen on TCP ports, such as web servers on port 80, mail servers on port 25. A machine that receives an unsolicited SYNAC. What does that mean? It means you weren't talking to anybody. When should you get a SYNAC? When you set out a SYN. But here's the thing, you didn't send one out. So if your computer gets an unsolicited SYNAC, means a SYNAC from somebody you weren't talking to, you respond with the reset. So you said, I wasn't talking to you. And if that was my computer that I got the reset, I don't need to respond to that. Does that make sense? Why I wouldn't need to respond to it? And if anybody's lost at any point, just say lost. And let me know where to start over. So if I get a SYNAC and I wasn't talking to you, I'm just going to respond with the reset. So one way to determine whether a server is open or a port is open or closed is by sending a SYN, and we get a SYNAC. Every IP packet on your internet, on your local network, wherever, has an IP ID. This is used for fragmenting packets. If I fragment packets and we need to reassemble them later, that IP ID says which pieces go together. The target machine will send back a SYNAC if the port's opened and a reset if the port is closed. Your operating system increments the IP ID for each packet sent. So what we're going to do is probing for IP IDs, and we're going to be able to scan somebody without our IP address showing up in their logs. Watch how this works. The first thing that we do is the attacker targets somebody else. This zombie is going to be, let's say, an iPad. How did I identify him? Through a nice, slow ARP scan. I had, a 4-hour flight. I had plenty of time to discover the network. So I send a SYNAC to the zombie, that iPad. When he responds with the reset, I can look at its IP ID number and write it down. Any question to that? Or any questions on that? So again, we send a SYNAC packet to the zombie. Every packet's going to have an IP ID. When the zombie didn't expect the SYNAC, he responds with the reset, disclosing his current IP ID, and we go ahead and we write that down. In this case, he said the response came back as 31337. Now in step 2, this is where spoofing comes in. I'm going to send a SYN packet, not a SYNAC, but a SYN to a target machine. That's the gateway. So if I'm on a plane or I'm at the airport and I want to look around, I'm going to send a SYN to port 80 on .1, which is the gateway. But I'm spoofing the source as that iPad that was sitting there idle. If the port's opened, he sends a SYNAC to the iPad. Let me use a different color pen so it shows up. So here comes the SYNAC to the iPad. What's the iPad going to do? He would act. He'd say, hey, I'm open. So what we do in this scenario, you've got the attacker, and the attacker sends a message to your gateway, which is .1, but he spoofs the iPad's IP address. Watch how this works. If the server is listening on port 80, he sends a SYNAC back to the iPad. The iPad says, I wasn't talking to you, and he generates a new packet, a reset packet, which causes the IP ID counter to climb. If .1 is closed on port 80 and a message comes in, it's going to elicit a reset. That means the iPad gets a reset. You don't need to respond to a reset, so in that case, the IP ID doesn't climb. Everybody okay with this? And then what we do as a third step is we probe the zombie again. I send a SYN to that iPad to the same port number, and I see how many numbers the IP ID went up. If it comes back as 31339, it incremented by 2, so port 80 must be open. If it came back as 31338, it must be closed. Everybody follow how that worked? Or do you want to see it one more time? Steve says it made sense. Got it. Okay, cool. So this is just a way. So if this device is going to have some type of engine on it, watching for port scans, he's going to think the scan is coming from the iPad, not from the attacker. And the attacker's bouncing him off the iPad just by leveraging the IP ID. Cool. So list scan is kind of dumb. Echo scanning doesn't matter. UDP scanning. So this is one last thing, we'll take a break. With UDP, you don't have SYNs and ACKs. So if you connect to a UDP port and it's open, there's no response. If you connect to a port that's closed, you get an ICMP unreachable message. So the way that you can scan a remote device for UDP is by sending UDP messages to different ports. You're not going to get anything from an open port, but closed ports are going to give you responses, which is going to be an ICMP error message. And then once again, this is that inverse scanning. So if I scan ports 21 through 25 and 24 and 25 reply, it means 21 through 23 are listening. Does that make sense? Anything that I don't get a reply for must mean that it's open. All right. In an ACK scan, this is real similar. This is what I talked about with looking for firewalls. If I send an ACK, just a TCP ACK to a port, like let's say that I did a full connect and it tells me port 80 is listening. And I go, cool. What happens if I just send an ACK to port 80? Well, if I get a reset for that, it means there's not a stateful packet inspection firewall. If I do a three-way handshake and port 80 is open, but when I send an ACK, there's no response, it means that there's a stateful packet inspection firewall, and he's silently dropping my packets without sending back a notification. That's just kind of a revisit about what we talked about earlier. Here's a list of do not scan IP addresses. Talked about that. And let's go ahead and break. When we come back from the break, we'll talk about banner grabbing, and then we'll start to get into enumeration a bit. So cool. How are you guys doing? Is everybody having fun? Hopefully learning stuff? Having a good time? If you're not and there's something I can do to make it better, let me know. But I hope you guys are having a good time with this. We'll go ahead and start our break, and I'll see you back in 15.